Welcome to Prime Numbers Part 4. At the beginning of this series, I mentioned I was planning on three lessons on prime numbers, but it turned out lesson number 3 was getting kind of long, so I broke it into two pieces. And there are a few more problems here. They're kind of hard compared to the ones from before, but I'll give you a solution to each one of them. For our first problem, find all prime numbers p and q such that p cubed minus q to the fifth equals p plus q squared. So I'll give you a couple of hints, and again, this is related to my solution. There's possibly other solutions, but I needed to use the rational root theorem. I'll show you what that is on the next slide, but if you want to kind of work on this before I go into the solution, you may want to look that up. And then the other hint is to just break this into cases for different values of p and q. Okay, so if you want to give it a try, pause your video now, and I'll come back on the next slide and give you the solution. Before we get into the solution for our problem, I want to introduce the rational root theorem, which we'll use in our solution. So the rational root theorem provides a method for identifying all possible rational roots, solutions that can be written as fractions or whole numbers, of a polynomial equation with integer coefficients. So let p of x be a polynomial with integer coefficients. We set it equal to 0, and we'd like to know what the roots are. The conditions are that each coefficient here is an integer. The first term, first coefficient, a sub n is not 0, and this coefficient here is not 0, and the other ones can be. If the polynomial has a rational root, x, p over q, where p and q are coprime integers, or relatively prime, then p is a factor of the constant term, and q is a factor of the leading coefficient a sub n. So this gives us a way of reducing the number of things we need to check to see if we have a rational root. I have an example here. This is a simple example. So the numerator, if we have a rational root p, we need to divide 1, so it has to be plus or minus 1. And then the denominator, q, has to divide 1, the coefficient here, and that has to be plus or minus 1. So there's only two possibilities, minus 1 or plus 1. We plug those in to p, put in 1, and we get 1 minus 3 plus 1 plus 1. So that gives us 0. So we found one root. Minus 1, however, is when plugged in, the p of x is minus 4, so that's not a root. So the only rational root is 1 for this equation. The other roots are either irrational, or they could even be complex numbers. You could find those by just dividing out x minus 1 into this and see what the remainder is. It would be a quadratic, and then you would solve that and get the other two roots. Okay, so let's use this in our solution to the problem. So let's start looking at some cases and see if we can exclude anything. We'll start with the case p equals 2 or q equals 2. If p equals 2, plugging that into our equation, we get this here, 2q minus q to the fifth, 2 plus q squared. Notice this is positive. However, on this side here, since q is a prime, q is greater than or equal to 2. So this is, when you raise 2 to the fifth power, it's 32, and that's the smallest it could be. So this is going to be negative, and therefore we can't have a solution here. So for p equals 2, there's no solution, so we can exclude this case. For q equals 2, plugging that into our equation, we get this here. Just expand this out. 2 to the fifth is 32, and then we square this. Then we take everything to one side, set it, and it equals 0. Then we can make use of our rational root theorem that we just talked about. So the rational roots are the divisors of 36 divided by the divisors of p, which the coefficient of p cubed, which is plus or minus 1. But we're only interested in prime solutions here. So that would just leave, and they have to be positive numbers. So that would just leave us with 2 or 3 as possible values for p, corresponding to q equals 2. If we put in p equals 2, we get minus 40 into this equation. And if we put in p equals 3, we get minus 30. So neither of these work. So there are no prime solutions for q equals 2. So we've eliminated 2 cases. We cannot have p equals 2 and we cannot have q equals 2. Next, we analyze the equation mod 3 to restrict possible values of q. So I just wrote our equation down here just to remind us. So we start out by assuming q does not equal 3. Since q is prime and it's not equal to 3, it can't be divisible by 3. Right? It would have a factor of 3, and that would indicate it's not prime. So q and 3 are relatively prime, and that means we can use Fermat's little theorem to tell us that q squared is congruent to 1 mod 3. So we have this here. Then there's another form of Fermat's little theorem that says that x, for any integer x, x cubed is congruent to x mod 3. And in this case, you don't need to have x relatively prime to 3. So we'll make use of both this and this congruence here. So next we reduce this equation mod 3. So we have p cubed is congruent to p mod 3 from this relationship here. So I'll just put in p here. Then I'll write q to the 5th is q times q squared squared. Since we know that q squared is congruent to 1, so we'll just get this as 1 squared. So these two terms just are p minus q. And I just bring this over here. Then I subtract p from this side and add q to this side. So you get 0 here. And we have this expression is congruent to 0 mod 3, which we can write as p squared plus p times 2q minus 1 plus q plus 1. Next, we'll test the possible remainders for p mod 3, And we'll find out that in each case, given this assumption here, we get a contradiction. And that'll leave us with the result that q must be equal to 3. So we'll look at this first one. If p is congruent to 0 mod 3, since p is prime, the only choice is p equals 3. And we'll plug that into this equation here. And we get 3 cubed minus q to the 5th, 3 plus q squared, and that becomes 27 minus q to the 5th plus equals 3 plus q squared. But this is negative. For any prime number, this is going to be negative. I mean, even if you pick the smallest prime, 2, you're going to get 32 from 27. So this is negative and this is positive. So there's no way these two could be equal. And so we have no solution in this case. Then we look at p congruent to 1 mod 3. And we'll work with this equation here, this congruence here. And so if p is congruent to 1 mod 3, p squared is also congruent to 1 mod 3. So we get a 1 for this, a 1 for p. And I just brought down the 2q minus 1 and the q plus 1. And if we add these things together on the left, we get 3q plus 1. But this is congruent to 1 mod 3, not 0 mod 3. So again, we have a contradiction. So these two cases are out. Let's look at the last case. P is congruent to 2 mod 3. Just plugging that into here, we get 4 plus 2. And we just bring down the q's. Adding these terms, we get 5q plus 3. And mod 3, 5 is just 2, and 3 is 0. So this is congruent to 2q. So if we have 3, if 0 mod 3 is congruent to 2q, that means 3 divides either 2 or q. But we know 3 doesn't divide 2, so this is implying that 3 divides q. But we assumed at the beginning here that q was not equal to 3, so we have a contradiction yet again. So in all three cases, we have a contradiction, which means our initial assumption was wrong, and that q must, in fact, be equal to 3. So we put q equals 3 into our equation. We have p cubed minus 3 to the 5th, and we have p plus 3 squared. Multiply this out, and then subtract it from this side. Multiply this, and then add the 27 to it, and you get this here. And then we use the rational root theorem. First, we want to see what this is in terms of its prime factorization, and it's 2 squared times 3 squared times 7. And so the possible candidates is only 7, actually, because you notice these are all negative numbers, so p has to be greater than 6 in order for this to not be less than 0. So the only choice we really have here is p equals 7, and we put that in there into this equation, and I've done the computations, and in fact it's 0. So p equals 7 is a root. We can look to see if there aren't any other roots. We know there aren't any other prime roots because the only other prime roots could be 2 and 3, but we can just check to see if there's any other roots. We really could just conclude it here, but if we factor this out, p minus 7, which I've done for you, and then if you use long division, you'll see it's this times this gives you this here. And if you use the quadratic formula on this, the b squared minus 4ac is negative. So in fact, this only has complex roots. So the only solution is p equals 7 and q equals 3. So kind of a long problem in order to just find the single solution here, but if we persevere as we have, then we find this to be the only solution. We have one more problem in this lesson. For distinct primes p and q, find the number of positive integers n less than the product p times q, such that n to the p power minus n divided by pq is an integer. And the source of this was problem number 5 from the U.S. Junior Mathematical Olympiad 2012. To solve our problem, we need to use the Chinese remainder theorem. I went over the Chinese remainder theorem in a lot of detail in a previous lesson from this playlist, and the title of that lesson was Progressions Part 1. So you may want to look at that if you haven't seen the Chinese remainder theorem before. I'll give you a brief overview on this slide. Let n sub 1, n sub 2, n sub to k be integers greater than 1. These are referred to as the moduli. And let n be the product of these integers. The Chinese remainder theorem asserts that if the n sub I are pairwise coprimes, so in other words, if you pick any two of these, the GCD is 1. And if r sub 1, r sub 2 up to r sub k are integers that are greater than or equal to 0, less than or equal to n sub I, for each I between 1 and k, then the system of congruences listed here has a solution x, and any two solutions, x1 and x2, are congruent modulo n. Okay, so we need a variant of this to solve our problem, which I'll show you on the next slide. We're basically going to shift the residues to the left side and the solution to the right side of the congruence. Now, you can always do that. Whenever you have something is congruent to something else, mod, whatever, you can always switch the two, because this is just saying the x and r1 are equivalent, equal, congruent is the best word, I guess, mod n sub 1. So let's look at the variant on the next slide. This is something I did not cover in this lesson here, so this is something new, even if you've been following all these lessons. Okay, so here's the variation of the Chinese remainder theorem. I call it the counting form, but I'm not sure if that's official or not, but you'll see why I'm calling it that. So we have the similar premise. We have this m sub 1 up to n sub k. They're pairwise coprime, and we let n be the product of these. Then the generalization or the variant on the Chinese remainder theorem says there exists a one-to-one correspondence between the integer x in the range 0 up to n, not including n, and the unique tuple of residues defined by. So you notice I've shifted, as I mentioned on the last slide. I put the solution here and then the residues on the left. This means every possible combination of residues, these r sub i's, maps to exactly one integer x in this range here. The consequence in terms of counting is consider a problem where a valid solution x must satisfy independent conditions modulo n sub I. So in other words, you have an x solves this. Let C sub I be the number of valid solutions for congruent size. So you would have C sub 1 solutions here, C sub 2 solutions here, and so on. Because every valid tuple of residues corresponds to exactly one valid solution x, the total number of solutions x in the range 0 to n, not including n, but including 0, is the product of the individual counts. So we just multiply the number of solutions in each case. Now for our problem at hand, and you'll see this in a few minutes when I get to it, we're just going to have two congruences, and we'll find the number of solutions for each one, and then we'll multiply those using this principle here. Okay, so let's finally, actually I have one more result that we need before we get to the theorem. I'll do that on the next slide, and then we'll finally get to proving or solving our problem. We need another result for our problem, and I'm going to introduce it on this slide. It involves something called a group, which hopefully you've seen before, but if not, I'll try to give you a quick definition here. A group is a set of elements with an operation that combines any two elements of the set to produce a third element within the same set. So this is called the closure property. And the following conditions must also hold. The operation is associative, it has an identity element, and every element of the set has an inverse. So identity just means whatever you apply the identity to, you get the same element back. So if the operation is addition and you add, for example, 0 to an element and you get the element back again, so 0 plus 5 is 5. In fact, the integers are a group, just to give you an example. And then the inverse just means when you add the inverse or apply the inverse to a given element, you get the identity. So talking about the integers again as an example, if we had 5, then its inverse would be minus 5. And when you add it to 5, you get 0, which is the additive identity. Another example, which is more of interest to us in our particular example here, and we've been kind of seeing this. I never called it a group, but we've been seeing multiple examples of the integers mod n. And in fact, that's an additive group. Now, for the theorem that we need, it's called the fundamental theorem of cyclic groups, and it involves something called a cyclic group. That just means that if you have an element in the group, that if you keep applying the operation to that element, you would generate every element in the group. So, for example, the integers mod 7 would be a cyclic group, because you could take, under addition, you could take the element 1, add it to itself, and get 2, and then add it again, and get 3, and eventually you get 6, and then when you hit 7, you go back to 0. So you've generated all the elements in the group. So that's called a cyclic group. And our theorem says, in a cyclic group G, generated by an element, little g, of order k, in other words, it has k elements, the number of elements x in G, such that x to the m equals 1, is the GCD of m and k. So let's look at an example to make this a little bit more concrete. We'll take our example I just mentioned, except under multiplication this time. So we'll take the integers mod 7. Now under multiplication, there's a little bit of a wrinkle, because the 0 element doesn't have an inverse. We need that to have a group. So this group here is 1, 2, 3, 4, 5, and 6 mod 7, but not 0. So this has 6 elements. And we'll take m equals 3, basically the m in this theorem here. As I just mentioned, this group is of order 6. And so the theorem tells us that the GCD of our m and the order of the group, which equals 3 in this case, there's 3 elements, x, in this group, such that when you cube it, you get 1. So we can verify that. 1 cubed is 1, so that's an easy one. 2 cubed is 8, and that's 1 more than 7, so that's 1, congruent to 1. 4 cubed is 64, and that's 1 more again, because 9 sevens are 63. The other ones are not going to work. The theorem tells us that. We can check one. So 3 cubed is 27, and so you have 3 times 7 is 21, with the remainder of 6. So 3 cubed would be congruent to 6 mod 7, but not 1. So that verified. You can check it for, I guess 5 and 6 would be the other 2 possibilities, but they're not going to work either. Okay, so we're going to need this in our solution to the problem, which I'll get to in the next slide. We're finally in a position that we can solve our problem, which I'll do on this slide and the next. The condition of this quotient being an integer is equivalent to the modular congruence n to the p minus n congruent to 0 mod pq. This just means pq divides n to the p minus n exactly. In other words, that this would be an integer in that case. Because p and q are distinct primes, and thus coprime or relatively prime, a number is divisible by their product if and only if it is divisible by p and divisible by q separately. So we have this here. Notice it's just the p now, not a p times q. And we have this here. Now in this first case, we can write this as n to the p congruent to n mod p. And that has p solutions by Fermat's Little theorem. That's the variation of Fermat's Little theorem. And in the second case here, we can rewrite that as n to the p congruent to n mod q, excuse me. So we need to do some work to analyze and find a number of solutions, n in this case here. So we'll take this and we'll rewrite it slightly, just taking the n to the left and then factoring out an n. So we have a product of two numbers, two integers, that's congruent to 0 mod q. So either one of these has to be 0. Case A, if n is congruent to 0 mod q, then we have one solution, that's n equals 0. If n is not congruent to 0 mod q, then it must be that this term here is congruent to 0 mod q, or we can write that like this here. To count the number of solutions in this second case, we look at the multiplicative group of integers mod q. This is a cyclic group of order q minus 1. And then we go back to our result that I talked about earlier. In a cyclic group of order k, the number of solutions to x to the m equals 1 is the GCD of m and k. In our case, k is q minus 1, and the exponent m is here p minus 1. Thus, the number of solutions for case B is the GCD of p minus 1 and q minus 1. Then if we add the number of solutions in case A and B, the number of solutions for our n, number of possible n's that solve this here, this congruence, is 1 plus the GCD of p minus 1 and q minus 1. So we're almost done. We just need to do a little bit more to finish this off. We'll do that on the next slide. To finish the problem, we need to make use of the variation of the Chinese remainder theorem I mentioned a little bit earlier. The counting form of the CRT guarantees that for every valid pair of residues, 1 modulo p and 1 modulo q. We only had two congruences for our particular problem. There exists a unique integer n modulo pq that satisfies both. Thus, to find the number of solutions in the range between 0 strictly less than pq, we can multiply the number of valid residues modulo p by the number of valid residues modulo q. So in our analysis from the previous slide, for modulo p, we noted there were p choices, and for modulo q, there was 1 plus the GCD of p minus 1 and q minus 1 choices. So we multiply these two together, and that's almost the solution. We have a little adjustment we need to make. The calculated total, this thing here, includes the solution n congruent to 0 mod pq, which corresponds to n equals 0, which is not a positive integer, or equivalently n equals pq, and that's not strictly less than pq. The problem asks for positive integers n strictly less than pq. This range is 1 to up to pq minus 1. The remainder 0 corresponds to n equals 0, which is excluded. All other residues combinations map uniquely to integers in the range from 1 to pq minus 1. Therefore, we must subtract the single trivial solution n congruent to 0 mod pq, and that'll give us our final answer. So we just take this and subtract 1 from it. Okay, so that was it for this lesson. It's also the last lesson I have on prime numbers. And I have at least one more lesson on in this series on Diophantine equations. And once I have that recorded, I'll put that up on YouTube.